Well, welcome to the Structural Modeling Conference for January 4th, 2020. Starting a new year and finishing up our run through and looking at ontology as a system at a very high level. We'll be talking about that today, and also starting a few new aspects of our work. One of the aspects of our work is basically we're going to start now circling back. I'm looking at some of the more dynamic work that we did in about 8 or so years ago, bringing in the dynamic parts of the matrix and behavioral operations. Then the other thing we'll be doing is starting to connect these, the logic and the dynamics together into a workflow and start looking at examples of how those would be applied. Fairly simple examples. The idea is to now start generating a set of examples and how these particular techniques would be used together to solve workflow and communication, system communication problems. So with that, I'll start into the ontology of the system part 2. And we discussed ontology as a system part 1 a couple of months ago. And then what we did was we actually looked at the ontology from the idea of context. We looked at basically what the performance, what ontology had to do, what kind of performance it had to have, like the metrics, how well, how would you know that it was performing correctly? And then we looked at the objects, basically the objects that were performing the required operations, as well as the metrics wanted them done. So that's the way we looked at it previously. Now we're going to use the general system cube and still looking at a ontology. We're looking at it from the evaluation viewpoint of structure, which is interesting. In the last paper, we did an overview of ontology definitions, and we decided to focus on the one by SOA, which ontology is a catalog of types of things that are assumed to exist in a domain of interest from the perspective of a person who uses language L for the purpose of talking about the domain of interest. The types in the ontology represent the predicates, word senses, or concepts and relation types of the language when used to discuss topics in the domain. So we like this because it had a number of references to the type of language. And what we're going to talk about here a little bit actually is the impact of language on the specific components and utilization and utility of a system. So let's see here. So one of the things that we've done is we basically decided to look at just the ranges of language, which is informal natural language to formal language, and then do a range of communicators from machine only to human only. And then along this plane, we've identified some areas where the type of language would impact an ontology. So one might argue that in area A, there is no ontology. It's just basically shared understanding and shared context. But usually everyone has an informal ontology. Kind of all understand that some of the same things exist. So I think the argument that there is never an ontology is weak. I'd say that the idea that there's never a formal ontology is pretty strong. So, but that's the idea of kind of defining these interaction spaces, and then start talking about what are the characteristics in these interaction spaces. So that's how language and communicators impact them. So what we'll do is then we'll talk a little bit about what an ontology cannot do. We'll discuss what restricts an ontology and constrains an application. Then we'll talk about general systems theory maps to ontologies and general systems theory and ontological development. Then we'll look at the relationship see what relationships create an ontology and discuss the attributes, and then a preliminary analysis of the part of relationship. We picked the part of relationship, which we took out of a reference work, which is applied ontologies. We'll talk about that a little bit, how that applies to augmented model exchange isomorphism, and then summary and conclusions, talk about some of the implications of this work. So up to that point, is there any questions? Okay, so what an ontology cannot do. So basically, you can't have a total ontology that's up to date all the time. There's some type of ontological work that's going to be some kind of lag. And that lag there'll be a difference between what people in the community are actually using and the documented formal ontologies. Or if it's not a documented formal ontology, then there'll be kind of a different view of the ontology informally among the group. So that if the goal is to have a formal ontology, that's always going to be behind. And then further, the ontology is limited by the knowledge of the people in the group. And so really you're going to have a collection of ontologies. And the more restricted a domain space, probably the better and higher fidelity you're going to have with an ontology. Looking at the work with, I think, Schwartz and Smith, the idea of what they have of a formal ontology relationship and what it's used for and its application is very similar to some of the basic ideas that were assigned for a general systems theory. So there is a very close relationship there. So one of the things that we looked at for this part, especially for human language and for informal language, were the 6 laws of language and linguistics in draft form from Gross, from Alexander Gross. And this is a very interesting discussion about linguistics and language due to the fact that Alexander Gross put this information together in a fairly compact way, as opposed to linguistics. A lot of linguistics literature is fairly verbose and huge, but Gross's 6 laws of language are fairly compact, kind of get the ideas across about what really restrains and restricts language use. And so the first one is the law of shared context, which all communication takes place in a shared context. And of course, if you have informal type of information, then you have the idea that people understand what that informal information means because they have a high level of shared context. And then you have the law of variable context, which says if people have a high enough density of shared context, almost any symbols can be used for communication, even nonsense symbols. And so that's it. From an informal standpoint, human beings, if they have a high enough shared context, they can communicate with nonsense syllables that are not necessarily have a strict syntax or a strict production rule set. So that's the difference between human understanding of semantics and machine or formal or applied mathematics types of formal languages. And I think that that's very important because that's the way we learn things. That's the way we create new language, and the way we go through and do disambiguation, figure out exactly what things mean. So it's really quite an important aspect, I believe, of informal natural language. But these laws basically, are impacted by ontologies because ontologies help organizing content and contextual concepts. So if now that they're organized, the ontology itself becomes part of the shared context, and people can talk about it, and they can talk about the differences between it, relating concepts in a well-defined manner, so that now that you're starting to aggregate these large number of concepts and relationships, then you can talk about them with just a name tag of XYZ ontology. And then presenting concepts and relationships in a standard fashion. I think this is really important, and from what I can tell, really still it needs a lot of work. There's not really a standard form for an ontology right now. There's lots of formal languages, but ontology themselves have so many different definitions and so forth that really this is an area where there could be some beneficial action, I believe, is in the standard. It's just making some fairly simple standard types of forms. And of course, Wikipedia frames a formal language, and a technical term is it's in mathematics and computer science, and it's basically a part of applied mathematics. And the applied mathematics would be such that it has a range of formal languages that can apply to a lot of different areas. So that's really important. In adding a range of formal languages to ontology creation workflows expands the number and types of ontologies that may be created. So if we mix formal language and formal ontologies with informal language and informal ontologies, it starts to create areas within the informal language that have a higher fidelity communication between the human communicators, and also are then become applicable to machine communication and machine language. And creating a situation where you can have a higher and higher density of these formal types of languages that are understood by human beings, I think is very important. Okay, so let's see. So figure 2 depicts communicators range from human agents to machine agents in the languages that extend from informal or natural language to formal language. And then it goes through and talks about areas that only have human beings, and they have a lot of flexibility in interpreting what those things mean in context. Then the idea that we have another area E, that only has machine agents and are talking with each other using formal language and formal application programming interfaces that are all very well defined. So 2 extremes. And in the middle, which we're more and more today, we find that we have a mix of the formal language and informal language. And these are things that are important, I think, to kind of just understand these buckets, define these buckets, so you can talk about what the impacts are. And of course, Area A would represent a scout troop with all the organization's rules, processes, and procedures, which is commonly shared context in their manuals and so forth. But each different scout troop would basically be able to fit their own value system, their own culture, onto what those rules mean. And that's, really a good way for natural language and groups to understand what their values are. But when you want to start, taking and putting scout troop information in a relational database, well, now you have a formal language interface, and you have to approach things a little differently. And then things become more and more formal until basically you have complete formal to formal interchange. Okay. So given that ontology is constrained by a specific domain of interest, as well as the specific language used to encode the ontology, the type of language used has a strong impact on the utility of any given ontology. So here, when we start looking at the definition of ontology, as looking at the definition of a system is a relationship that is associated with a set of objects, or a system is a relation that's mapped over a set of objects, depending if you want a formal or informal type of definition. Then things start aligning a little bit more. And so what we want to do is we want to find an ontology that we can use and have the tools either for a formal language or an informal language that fit our goals. Like, what really do we want to do in this particular activity? And is it better to have use a formal language or an informal language, or both? And one of the things that the AMEI supports is it supports the integration of informal language and formal language. So the model exchange isomorphism that was done by Warfield was an exchange from mathematics to structured graphics. And so the three basic primary components of language that was proposed by Warfield was prose, structured graphics, and mathematics, or a combination of these primary languages into composite languages. So what Mary and I did was we just started and we added prose to the model exchange isomorphism, call it the augmented model exchange isomorphism, so that you could map a specific natural language concept to the mathematics, the logic of the matrix and the structured graphics. So this became an isomorphic form. And that isomorphic form would also be negotiated among the different groups exactly what that meant when it was applied. But it becomes much more formal. And we've talked about these, the application of the augmented AMEI and the art form in a number of publications and how they relate to other systems analysis types of techniques and systematic complexity reduction techniques. Now, we believe that the AMEI reduces complexity because it reduces uncertainty. Things are mapped. You have a one-to-one or a one-to-many mapping between these types of places or these types of logical groups, and then the logic of that group in a specific context can then be discussed. So it really provides a very nice framework. And so the structural integration, strengthening the foundations of system science is one of the areas where we talked about this. Enhanced reachability matrix is another area where we talked about how you go from an informal language to a formal language transform, and what components need to change and why, and how the computation is used in the forward transform and the backward transform. And we also went through and looked at the inclusion matrix, the subordinate matrix, and the adjacency matrix. Now these are natural language concepts: inclusion, subordination, and adjacency. and they are mapped to formal constructs, formal language constructs. And what we found here is that basically there was, in the inclusion and subordination are okay, but the adjacency matrix had some issues with it from a natural language standpoint because of the logical properties that were assigned. We discussed that in that paper. And there's other areas where we find that looking in the systems analysis and systems evaluation literature where there's appears to be a conflict in the logic that's applied to the natural language. But with the natural language, sometimes it's difficult to know because the natural language isn't precise enough. One of the key factors of the AMEI is you're able to assign a tag, you're able to assign a specific tag to the natural language relationship that will assign a logical group to that specific natural language phrase. And so it can become much more well-defined. And so that's a mechanism by which natural language communication then can be tagged and made more formal and more precise. So as we were looking at the definitions of ontologies and doing an overview, we found that some of the literature assigned functions and goals of an ontology or general ontologies to basically what you would were assigned to general systems theory. And we started looking then at that viewpoint, looking at that idea, looking at that insight, saying, well, okay, then if general systems theory is the name that's come to use to describe a level of theoretical model building which lies somewhere between the highly generalized constructs of pure mathematics and the specific theories of specialized disciplines. So I'm talking about formal ontological relationships. People are saying, well, what we have is we have applied mathematics, which is not theoretical mathematics. It's not pure theoretical math, so it becomes an applied, which puts it in general systems theory, but it also is portable. And so it can go between different disciplines. And so it seems like they're starting to talk about a formal ontology relationships in the same way that general systems theory was discussed in the past. And the value that's associated with this formal ontology is saying, well, it's the same thing as the value that was assigned with general systems theory was we can now identify things that are common in all these different areas. And we can identify the commonality and reduce the complexity because we know they're the same. That becomes a very powerful concept and a very powerful tool if it's implemented. And so the AMEI and the art forms are basically put together to help as tools to help in the evaluation and communication of these ideas. The abstract relation type was put together to focus on the relation formally between between the objects in a system was the start, but the same thing can be applied to an ontology. Talk about those relationships, how the things in the space, how these concepts, how are they related to each other? And this can be looked at in abstract relation type is a very adaptable mathematical form. You can have a marking space, an outcome space, multiple value spaces. You can have multiple marking spaces, multiple outcome spaces, and multiple value spaces. not constrained. And then you can analyze these on any different dimension you want. You can have different values and different functions on the different dimensions. And then you can integrate abstract relation type once you identify a specific component or a specific system or a specific ontology that you want to analyze and put it into the art forms. Then you can actually integrate the art forms in a number of different ways. It can be done by sparse matrix type of manipulations. There's time series type of manipulations. There's a number of different ways that can happen. But once the matrix form is put together, then that becomes a very efficient way as kind of a, let's say, a memory of an artificial memory that you can use for the analysis, and you can use to support all types of artificial intelligence operations. Because if you look at the machine learning and AI, really the primary aspects that are happening there are the fact that, some people say all AI is large-scale search. So you're searching, looking for some type of value, looking for some kind of pattern, looking for some kinds of connections. And so the thing that's going to restrict your search is restrict the effectiveness of your artificial intelligence is how efficient is your search? What about your memory constructs? What type of algorithms do you use in the search through these matrix spaces? And those are things that, well, we've talked about in the past, and we're going to now start reintegrating again in the near future. So just again, it's interesting to note that the range and strength of similarities among the concepts associated with the ontology, the art form, and the GST, so that they are looking at things that are common across different domains. And so highlight and reinforce and communicate these similarities and what the values are. That's one of the goals. So what relationships create an ontology? So basically, an ontology has been talked about as a knowledge graph, can be represented as a knowledge graph. So here we have an informal and a formal definition of a graph. And the what we start talking about here now is saying, well, what happens when we have the same relationship but different objects on the nodes? Or what happens if we have the same relationship and the same objects on the node? And the idea is there, it's like part of. Well, if we have a part of ontology, that's going to relate to many different domains. But if we have specific instances of parts that are on a graph, then those are probably going to be much more restricted and not as portable. So those are some of the things that we'll also look at in the future. But Swartz and Smith, the authors of Chapter 10 on ontological relationships in the book, I think, Applied Ontology, said the relations mentioned are genuine formal ontology relation. That means first that they are ontological, not merely logical. So I looked at this and said, well, okay, this must mean then that all ontological relations are logical. They have some logical components to them. Then need to work on understanding what they mean by ontological. What are these attributes? What are these characteristics? How do we tell an ontological attribute from a logical attribute from a non-ontological attribute? How do we make this distinction? And that's, again, something we will be working on as we go forward. And it says here, this is an interesting statement because it implies that all formal ontological relations have a foundational logical component. And Schwartz and Smith talked about part of as their example. And the examples they gave, they said part of is a primitive part-whole relationship between two constituent instances, or it's a primitive part-whole relation which is independently of time obtained between two process instances. Okay, so there's two things and there's a relationship between two things. Is basically what they're talking about here. And so these part of relationship clearly binds, these two objects together. But then they go on to say, well, that the part of relation, we have the following from Simon. This relation is irreflexive. No entity is a part of itself. Okay. It's anti-symmetric, that if X stands for the part of relationship to Y and Y stands for the part of relationship to X, then X and Y are identical. So this says basically the part of relation is not a part of relation, which is quite confusing because X and Y are identical, that's equivalence, and has a completely different set of logical attributes. And if you use a part of relation to try to draw out, X is a part of Y and Y is a part of X, that is really logically confusing. What does that mean? Anti-symmetry, in this case, is again quite confusing, and it introduces a lot of uncertainty. And then, so on page 233, the authors present a graphic, and again, they give the logical attributes for part of, which is transitive, asymmetric, reflexive, and anti-symmetric. So now they've gone from being irreflexive to reflexive. And now there's internal conflict of the logic components within the body of the text. And it's not clear that the authors, we're saying, yes, we really mean that you can have a transitive, asymmetric, reflexive relationship, part of relationship, and the part of natural language part of relationship just isn't enough to, isn't clear enough, or doesn't have the fidelity to communicate what we really mean. And if that's the case, then you start breaking down, well, what do they mean logically when they talk about this? And it becomes very confusing. And the AMEI addresses these issues by charting out 27 different logical groups and assigning and talking about these relationships and what they could mean. And so it's a way that the AMEI helps decrease uncertainty and therefore decrease complexity. Besides, of course, the logical relationship groups, we've identified other attributes that are important. And one's a global attribute and the local attribute. And what do those mean when you're talking about a relationship between objects? And so these are, not sure if that's what the ontological authors were talking about when they mean ontological. I think they were talking about more like universal and individual, but again, that's another area that kind of needs to be adjusted to see if those match up. See if you can actually do a little bit more of a mapping there. And so the part here is the include-in hierarchy of math theories. We just did this to show that if you have your base logical attributes, asymmetric, symmetric, irreflexive, reflexive, transitive, and intransitive, then how you combine these individual ones. You can combine them 2 at a time, or you can put them up into 3. When we get 3 at a time, you get strict order and equivalence. When you get 4, where you have anti-symmetry and strict total order, you start having issues because there are if statements. You say if this, then that, and that introduces uncertainty into these compound logical rules that have 4 or more components. So we restrict, at this time, we restrict the logical evaluation to 3 or less, because there are no if statements, no uncertainty down here in this area. And again, we use the, so it says, while the concept of formal ontological relations is appealing, considered a valuable addition to the ontology toolbox, it's not clear the approach outlined by Schwartz and Smith contains the necessary rigor and or formal foundations to deliver this additional value. So it's kind of confusing once you try to really break down formally what these guys are saying, just about the part of relationship. And it's interesting to me that system scientists and logicians and people over a period of time have been working with these concepts, and there's still not a clear definition of what part of means logically, or a way to say, well, it means these things in these different contexts, but it specifically is this here and that there. And fundamentally, the AMEI allows that. It is a binning. It's got 27 bins, and it says it's going to fit in one of these bins. What does that mean? And of course, in the AMEI is kind of a static logical mapping, where the art form allows dynamic mapping. Okay. So basically the part of natural language relationship demonstrates the use, value, and application of the AMEI art forms. And so many system science engineering tasks use mathematical functions and formal language to evaluate these models. And especially when we're going to start going to the dynamic models, the mathematical formal pieces become more important. And there's a map back and forth. Now we're developing a map between natural language to the formal language, and that goes through the auspices of the AMEI. Starts reducing uncertainty, reducing complexity, and increasing the fidelity of our communication. And what we do is basically provide a tag. So if you really mean part of, right, and you mean it's irreflexive, asymmetric, and transitive, and you're having a formal discussion, then you can actually tag it. You can say, okay, part of IAT. And with that type of tag on that type of relationship, then you can have a formal language that interprets it, parses it, and assigns the correct operations. But then also the author said, well, part of reflexive, asymmetric, and transitive. And then they also assigned the anti-symmetric property. And the reflexive, asymmetric, and transitive really raises a tremendous amount of issues and questions logically. Like reflexive applies to only one object. So in part of, are we only talking about one object? The wheel is the part of the wheel. Well, okay. So when we say it's asymmetric, so that means, the wheel is part of the wheel, and or a wheel is not part of the wheel, because that's what asymmetric means. So there's a lot of uncertainty introduced when communicating what that means, and it's not addressed. So if they actually meant that it was reflexive, asymmetric, and transitive, it's not clear what impact that has in interpreting in reality. And again, we've already talked about the issues with the anti-symmetric property interpretations. And so our way has been to just, restrict our attention to the fundamental logic that can be interpreted. And the idea really is to do this so we can go over a large group of people, and that people can quickly understand it. We're We're trying to eliminate the confusion. We're trying to eliminate the uncertainty and still achieve this communication about the same types of relationships, but only at a much higher fidelity. And part of doing that is by decreasing the uncertainty. Okay, so we talked about the logical, so that, if the part of is reflexive, asymmetric, and transitive, appears that a logical contradiction is produced. A number of them, depending upon how much detail you want to go in talking about what appears to be absurd with that specific assignment of logical attributes. And again, we talked about the anti-symmetric property and the issues with that. We're not saying that the anti-symmetric property has issues everywhere. So we're just saying that, if you're going to assign the anti-symmetric property to a specific natural language relationship, it needs to make sense within the context. There may be formal, high-level mathematical relations that the anti-symmetry makes the tremendous amount of sense. That's fine. But we're looking at this from an applied mathematics formal language. And in some cases, it does not make sense. So the AMEA combined with the art form, again, can increase the fidelity of systems engineering and system science communication by transforming informal natural language relationships into formal relationships. So when you start looking at it at this level, you're looking at what's going on, you say, well, people never make these kinds of, of logical, mistakes. But in our work and looking at doing the literature search and literature studies, we have found a number of areas where people look at the mathematics and make statements about the mathematics that are just absurd. And we have, of course, early versions of that where people say, well, we're analyzing events that happen in sequence, and we apply these logical transforms. And because we apply these logical transforms to our mathematics, that means these events, precede themselves. Well, if that was true, what does that mean? So if I'm going to take information about my reality, empirical information, put it into a mathematical transform that says, events can precede themselves, and it's give me some output. What in the world does that mean in reality to us? I mean, that basically layers tremendous amounts of uncertainty and just doesn't seem to have any utility. But people built a complete, process and idea on that type of mathematics. Again, here where you find, like with the Smith and Schwartz, these folks, they're mixing up these logical attributes, and it's not clear what they mean. In one case, it's fairly clear what they mean, and the other case, it's not. Again, it introduces more uncertainty, and we don't really have a mechanism of talking about that. And there's other instances, documented instances, where people have used the logical attributes and relationships in such a way that it was basically just turned out to be highly uncertain and what you might consider nonsense. So out of this, the summary and conclusions in this particular work we're in, basically we demonstrated an application in the General Systems Cube, a little framework we can use to talk about structured viewpoints as different systems. And we used PMO last time. We used the structure component this time. And the fidelity of system communications can be greatly increased using the AMEI and the art form. But we need to, be careful about informal human language interface and formal machine interface. And this is going to be much more important as time goes on because machines are going to be everywhere. Well, basically everywhere now. And it's going to help people to carefully and clearly communicate between themselves and other agents. And so what was interesting to me is many of the current goals of formal ontology development are the same goals that were assigned to the GST in the 60s and 70s. So that's an area where get some time. I'm going to go back and look at that. And what Mary and I are doing right now is we're kind of, again, finishing up on our first cut through this formal analysis on logic that Warfield put together. And now we're going to cycle back to the dynamic components that we did about 8 or 9 years ago. And we're going to start integrating these as we go forward. We're going to do that with using a little bit more computationally intensive approaches and analysis. So and we're going to be taking those and putting them more into a formal type of research questions and also generating some hypotheses and doing some calculations and putting them a little bit more in a standard form. So are there any questions?
Excellent. Thank you very much. I've kind of collected about, I don't know how many questions in my head over the previous 45 minutes. So that's why I'm being selfish and jumping in. I mean, first of all, it's excellent progress or presentation of this topic. And I think that the way you've put the system cube together and the ontology is extraordinarily helpful. I'm thinking in context, well, many contexts. And I guess the question I have is that, you know, you talked about utility and practicality. My interest is in system literacy. And I'm wondering about how with the AMEI and the ART, when you began, you looked at an evolution from informal to formal, and in your conclusion you sort of stopped with that. I'm wondering if there's a circularity to it that you could explore. So formal to informal, I mean informal to formal to back to informal, so that you're in a loop which is iterative and a learning loop in a sense. But I guess my main question is there a natural way to think about using what you're doing here as a design framework, like for systems literacy in terms of evolving language? Or another challenge I have at the moment is to help design an international network of scientists who are working on identifying, measuring, reporting on life in the sea, and that therefore, you know, there is some thought perhaps that an ontology within a general systems cube, or, you know, in some way could help us understand the language, informal, formal, natural, whatever, that's used to describe life in the sea, which of course is a crucial component to us understanding life on Earth and our future. So I know that's a lot of comment and questions all intermingled, but that's guess where my scrambled head is at the moment.
Well, Peter, I think first of all that the idea between the informal language and the formal language, the utility. So why do we want to do that? So we want to do that because we want to facilitate and give the human beings and the human intelligence the tools they need to do their best and work in the areas where they are very, very good. Then we also want to give the artificial intelligence or the machine learning, we want to put that together in such a way that it has the capability of doing what it is really, really good at. And the large scale search, okay, within the matrices and within the art forms, that gives a tremendous amount of large-scale search capability for a machine. But the key thing about the art form is you can break it down in a very structured way so a human expert can find their part in that plane. They can find out where they fit in. And so increasing the fidelity across that is very important to make sure that you get some reasonable understanding. But you can have the large-scale search from the machine side augmenting the human intelligence. As far as the design goes, of course, this is all based on Warfield's work in the science of generic design, right?
Right.
And so the design values from the human standpoint, the design values that you talked about, then you would have the groups start developing their value system. And of course, that's what Kevin is an expert in helping people do that.
Yeah, I'm just thinking about using the ART and the AMEI as a guide, or is there a natural progression? You've got the 27 boxes, or if you will, the matrix. But is there a growth curve? Is there a development curve or trajectory through various types? I guess is my
okay. So I think maybe the idea where we talked about the inclusion matrix,
yes,
the adjacency matrix,
yes, exactly,
and the subordination matrix.
yes.
So those are all kinds of things. So there's also the idea of a priority matrix.
Yes, exactly.
If you had a group, and you're going to, okay, guys, what are our priorities? How are we going to order these things?
Mm-hmm.
Then there's also a curriculum matrix.
Mm-hmm.
These are all operations and all application structural types that are documented by Warfield in his literature.
Right.
So these are specific aggregations of types of operations. So when we look at a concept, a relation, let's say priority, A has higher priority than B, right?
Right.
So you would say higher priority of that relationship, you would map that relationship to the AMEI. And that AMEI mapping would basically be the way that the guys that are doing the work, that are actually have the human intelligence and are talking to each other, then you could come up with a simple set of rules so that they could ask themselves some questions, and intercommunicate quickly and focus and calibrate themselves on what that specific relationship means. Then you take that block in the AMEI and you hand it to the coders, and the coders then can code up the software that will basically impact that and interpret it correctly. And the reason what we found is when we went and looked at this, we found it mismatched all over the place. So there are already types of application structural types that have been put together, and you can find in Warfield's literature to do and support the types of things that you're talking about.
Okay.
The primary problem is the software to do it is not available.
Right.
And so that's kind of what we've been working on. We have some that can support it. We have
even the manual process. I mean, I'm just thinking now. I'll go back and think about Warfield's work in this context. But I guess I was just even thinking about procedurally, without a computer, even.
Right.
There would be some. I mean, you had those 4 levels diagram, which I liked, where you had the 6 on the bottom, 6 types on the bottom, and then you went through. That had a certain logical structuring that could be helpful in that.
Yeah, it's all there. It's
exactly.
And the idea is to but the type of task that you're talking about, it to me seems to almost be perfectly aligned with what the science of generic design was designed to do.
That's why I keep turning up here.
Okay. Kevin, do you have any comments on this?
Can you hear me?
Yes.
So, if you're modeling zoology, how to go about modeling the relationships is a subject of a journal called Systematic Zoology. And they had about 25 years ago, I had a few months to follow a particular debate in that journal about the relationship. What is the logical properties? What's the appropriate logical properties of the relationship of, genus and species? And a guy named Nelson Goodman came into it. He came into the debate and kind of settled it, at least for the zoologist. And he later wrote about it. He called the issue the problem of imperfect community, right? And so, if you have something that is like something else, let's say A is something like B, and B is something like C, what can you infer about the relationship of A and C? If you're talking about similarity, sometimes it could be transitive or mesotransitive or non-transitive. And so this is where the debate went. And he eventually came up with a formulation that satisfied people, which is if you model things in terms of asking the question, is A and B more similar to each other than B and C are? And anyway, there was a book published about it called The Structure of Appearance, and that covered a lot of that debate for property in modeling. Now, they didn't call it ontologies then, because this work was kind of concluded by the late 50s or so, or by at least Goodman's work. But it might be worth revisiting that. And I just remember that we did a session or two specifically on the logical properties of part of relationships from the studies of mereology. And like in that presentation, this work by other people that I was presenting, there was at least a dozen different logical combinations of logical properties for representing part of that were used for different purposes. And some things that don't seem to make sense, like is it appropriate to have a logical system in which the part of relationship has a reflexive property, i.e., is it appropriate to think of a wheel being part of a wheel? But there are logical systems in which something is a part of itself. And it makes a lot of sense to have that, to have a reflexive property if you want to model fractal systems, because a fractal is a part of itself. And that's where and it's asymmetric at the same time as being reflexive, because you want to be able to describe different levels of fractal systems. So it depends on what you're modeling. And there's been a lot of work, just in this kind of obscure branch of mathematics called mereology. And one of the problems is, people writing about ontologies, a lot of them never bothered to look at what's been done 50 years ago. And but because it's from a different field than they're familiar with. So anyway, it might be useful for us to.
Kevin, we have a few minutes left here, about a minute or two.
Yeah.
Would you see January 18th, 2 weeks from now? Could you continue on and kind of give a presentation 2 weeks from now on that?
Yeah, I think it's a nice complement to the part of relation to talk about kind of the similarity or kind of relationship and logical properties of that. So that'd be good.
And so the idea really is, as I agree with you, this work has been done in the past. The component here is to calibrate the group, the human group, with the formal component. So I would say that if you had a group of 50 people that were working together on the idea of part of, you wouldn't want them all to actually have 50 different interpretations. So the idea is to basically start, with like the AMEI gives you your buckets, gives you things to talk about, but also questions and answers, and people can then start formalizing and start becoming more, adjusting or calibrating their view. And so that if you have a group that's working together on a certain thing, then they have a higher assurance that they're all kind of mean the same thing. And then once you have that assurance, then it can go across, and you can basically then have a mapping to more formal types of implementations. So that's, and you can change those formal implementations given the context. And again, that's what the AMEL allows you to do. It's kind of, kind of a little map thing that you can do to help calibrate the informal language and then design the formal language. So it's kind of a language design transform. So we'll look forward to your presentation on January the 18th, Kevin, on this. And is there any other final questions, comments? Well, then that'll do it for our first event of 2020, and we'll see you all again on January the 18th.
Thank you very much.
Very good.
Joe,
Bye-bye.
Mary.
Okay, bye-bye.